Okay, so I will start the session. So, welcome all of you to our eRides webinar series. My name is Maitri Pitroda. I'm Associate Program Manager in PR and Marketing at eRides and C1973 EV Lab, IIT Bombay. So, I will give quick introduction about the organization, then our speaker of the day, and we will start with the webinar. So C1973 EV Lab Powertrain Lab at IIT Bombay is a donation project by Class 1973 BTech batch. So it leads innovation in electric mobility, advancing critical EV technologies like motors, motor controllers, and battery management systems. So it mainly focusing on developing advanced solutions to enhance the performance, efficiency, and sustainability of EV powertrains. And it also provides educational programs and networking opportunities. So, talking about the eRides webinar series, so eRides it's a project like IIT Bombay has been selected as e-node under the Maha EV mission by ANRF. So it collaborated with six institute that is IIT Kanpur, Delhi, IIT Bhubaneswar, IIT Gandhinagar, SVNIT Surat, and with 22 industry partners. So this this drive innovations in India's electric mobility sector, with mainly focused on power electronics, machines, and drives. And this project aims to bridge the gap between like academic research and industrial needs for the next generation of EV technologies in India. So under this project, we have launched this eRides webinar series. It will be monthly sessions. Every month, one webinar will be there, which experts will share insights on emerging trends and innovation in e-mobility. So, today is our first session of this series with the speaker of Dr. Pallavi Bhardwaj, Faculty of Electrical Engineering at IIT Gandhinagar. So, I will give quick introduction about Miss Dr. Pallavi Bhardwaj, and I will go through the webinar flow and I will hand it over to Dr. Pallavi Bhardwaj. So, our speaker of the day, Dr. Pallavi Bhardwaj, is Electrical Engineering faculty at IIT Gandhinagar. She has previously served as faculty in Aalborg University, Denmark. She completed her postdoctoral research at MIT, USA in 2021 after receiving her PhD from Indian Institute of Science in Bangalore. So Miss Pallavi is also a gold medalist for her industrial training and has received several awards, including POSCO Power System Award, Bhaskara Advanced Solar Energy Indo-US Fellowship, and also serves in national and international technical committees since 2017. So she is very passionate about the sustainability and strives towards engineering optimized solutions for global energy needs. Her research interests broadly include design and control of renewable power converter systems and modeling and optimization of energy storage solutions. Physics inspired AI for smart power electronics towards net zero transition. So, this is the brief introduction of our speaker, Dr. Pallavi Bhardwaj. And today's format of webinar is very simple. Dr. Pallavi Bhardwaj will start the session about, it will be around the 40-45 minutes. And at the end of the session, for 10 to 10-15 minutes, we will conduct Q&A sessions. So till then, if any questions during the session, please post your session in the chat box. And now I will invite Dr. Pallavi Bhardwaj to start the session. Thank you so much.
Thank you so much, Maitri. I hope I'm audible and my screen is visible.
Yes, ma'am.
All right, perfect. So, hi everybody. Thank you for showing up on a weekend. that too near the exam week. So yeah, I am a part of the E-Rights Consortium. Very happy to be here. At IIT Gandhinagar, we have this forte on safety. We have a Center for Safety Engineering. So even in our Maha EV project, we have brought this new dimension, which is on electric vehicle safety, especially with the energy storage devices, may it be batteries or any other kind of storage device like fuel cells in the future. So this is kind of a chemistry agnostic system that we are making. And of course, we have a very, very strong team here at IIT Gandhinagar and a very big and strong team across different IITs like Maitri and SVNIT like Maitri introduced before, along with a very strong industry consortium as well. So let me start by giving an overview of what we are up to and how was my journey so far. So I started with my bachelor's in engineering in Delhi and I graduated in 2012. Then I went to Bangalore for my master's, followed by, I really loved research at that time when I started my PhD in the same department, electrical department in ISC. Towards the end of my PhD, I was invited as a Fulbright Fellow and I went to Boston as a research exchange student. At that time, some of the MIT faculties had a good interaction with me and they decided to offer me a postdoc. And I stayed there for then 2.5 years, 2 years for postdoc, 6 months during the end of my PhD. And then I was invited as a faculty in Denmark. But I always wanted to work for India, and the first IIT whom I had applied to, and the only IIT I had applied to was Gandhinagar because it was working very well for my family. So they gave me an offer in October 2022, and I joined immediately because I was very, very excited to come back to India and advance Indian science and technology. So the year that I came back was 2022, and like I said, right? So it was around the Diwali time. But there was another kind of Diwali that was going on, not very promising. So it was a milestone year, in fact, for electric vehicles in India. Many players were coming. Ather became very popular. Ola was coming, Hero Electric. So many companies had started developing. Even many startups started coming in the ecosystem of electric vehicles. But something very interesting we observed, at the same time, because many of the battery cells were being imported, a lot of converters were just assembled without proper design, proper battery management systems in place, especially for Indian conditions like high temperatures, high humidity conditions. It was observed that these vehicles were catching fire, and the kind of trust that we wanted the community to build around the EV transition from the conventional vehicles was breaking out, right? So we thought, what can we do to make this better? But the country is extremely resilient. Our Indians are extremely resilient. Even though those incidents happened, still there was an amazing growth rate in terms of electric vehicle market in India. So it is observed that EV market is the fastest growing market in India. And across the last 6 years and coming 6 years, if you look throughout that duration of 12, 13 years, we are the largest market, right? And also growing at a very rapid pace. So we have players like Tata, we have MG, Mahindra, so many players, and even now Maruti Suzuki has come into the business of EVs. So many major players are transitioning, and other foreign companies are also very interested in setting up their shop in India, like Kia, etc., Hyundai, etc. So, given the statistics, EVs are not going anywhere, even though they were catching fire in 2022. Still in 2025, 2024, it was the largest EV production year last year, right? So even with small hiccups here and there, the country is so resilient, the market is so strong that EVs are here to stay. They are not going anywhere. So we should think about how to make them more reliable and more safe for our community. That was our motivation. So let's try to understand for the generic audience here what exactly is inside an EV and what are the common type of EVs that we'll be addressing in today's talk, right? So one of the very common EVs is a Tesla. So Tesla Model 3 became one of the very, very popular cars in the West, especially in the US. So when I lived in the US, whoever owned a Tesla was considered very smart, because the performance is amazing, the AI for Tesla is amazing, etc. Then Japanese makers are always on top of the automobile sector. So Mitsubishi Outlander, which is a hybrid electric vehicle. So plug-in hybrid electric vehicle means that you can charge it with a battery at the same time you have a petrol or a diesel as a backup fuel. So sometimes the hybrid vehicles have the main fuel as as the fossil fuel, and battery is only there for regenerative braking, for example, or extending the range or making it more green, like that. But it depends on the vehicle. How much is the percentage of the fossil fuel or how much is the percentage of the batteries? So that would make it mild hybrid or strong hybrid. So typically, what is the problem of the safety? Actually, the battery packs are kept at the bottom of the chassis, right? So if you have an entire vehicle, at the bottom of the vehicle, you see the battery pack is there. Now, if there is any accident or any kind of penetration because of ground clearance being low or whatever, these batteries tend to become short circuited from inside, and therefore they catch fire. Okay, what are the reasons? We will be discussing them in a minute. So essentially, these batteries are cells, lithium ion cells put together in series and parallel combination to get the required ratings. Uh, these cells can be cylindrical, prismatic, or pouch in the packaging depending on the application. In Tesla, for example, they use cylindrical cells still, and the active material of the cell is called a jelly roll, as you can see here. This jelly roll essentially has anode, cathode, electrolyte separator, everything rolled together. Okay. So if there is a penetration, what happens? The separator gets penetrated and there's a short circuit between the cathode and the anode. And therefore, once there is a short circuit, very high currents flow, it causes ohmic losses. And there are also exothermic losses that we'll be talking about in a minute. That causes a fire incident. Okay. So it is not that we don't have a EV safety, ecosystem in India, but because it is a new industry, not like the conventional automotive industry, which has been there for several, 50, 60 years, this industry is maybe 5, 6 years old. That's all, right? So the ecosystem is still building. So we have BIS, our Bureau of Indian Standards, which has been making several standards in consultation with academia and with industry. The idea there is that these standards should take care of the vehicle safety, battery safety, and together vehicle and battery safety for different kinds of vehicles, like small vehicles, large vehicles, etc. So the ecosystem is building up, and every time there is a new input or a new factor in the market affecting the health of these systems, these standards are also revised. Okay. Many of the standards, however, are only some of them are mandated, but not all of them are mandated. So this is something that still is getting evolved as we move, because this is, like I said, a very new industry that we are dealing with. Just to brief the audience about what are the kind of standards or the tests that a vehicle and a battery pack has to go through before it can be categorized as a safe battery pack to be put in the vehicle. For example, for light electric vehicles, which are called as L category vehicles, like two-wheelers, three-wheelers, you have to do several tests like vibration, mechanical, fire, thermal test, overcharge, over discharge, whether it has some vicious gases coming out, etc., how safe it is. If it's a bigger vehicle like a four-wheeler or a truck or a bus, etc., MNN category vehicles, the tests become even more intensive. For example, you will have to take care of even thermal propagation because it's a big battery pack. So if there is a hot spot in one end, it can propagate to the other end or not. So then the propagation would come into picture. Another test which may not be there in smaller vehicles but is there in larger vehicles is a mechanical integrity test. So if the vehicle is moving through a speed breaker, for example, if it goes up and down, does it break the battery pack? Does it strain it? So there are many things that are coming in place as we talk, they are evolving. So let's try to understand why these lithium ion batteries in electric vehicles are so risky, what is the real deal here? So essentially, thermal runaway is the process where the heat generation inside is much more than the heat dissipated. So eventually, the temperature of the battery pack increases to an extent that it catches fire. Huh? So, how does that happen? It can happen through internal issues or external issues. So, internal issues could be there could be defects, there could be some kind of self-heating ignition inside the battery, maybe something happened, or it could be external like overcharging, overheating, so electrical abuse, thermal abuse, mechanical abuse like an impact if there is a let's say there's an accident, so the chassis of the car got injured, so then there could be mechanical abuse as well. So what happens because of these cases is that lithium ions are essentially moving from anode to cathode and cathode to anode in a charging and discharging process. In this process, sometimes they react with other elements like the electrolyte, ions, etc. And they make something called as SEI, the solid electrolyte interface, right? Also, when they bond with the neighbors in the cathode, and metal oxide is there, no, on one side. Those who are from chemistry background can appreciate it. Other background people just take it as general knowledge. I'm throwing another fact at you. So what happens is that because of this movement of ions, there are some exothermic reactions. So exothermic, by the name itself, you can see that it is taking out energy, right? So heat is given out as a part of this reaction. Now, very interestingly, when there is any kind of abuse, these side reactions, like I said, SCI growth, etc., they increase. When they increase, the heat becomes even more, right? And when the heat generation is more, the temperature rises. And at higher temperature, the reaction rate is even higher. So it's a vicious cycle. Okay, that is the reason why we have such high propensity of thermal runaway if something has gone beyond the tolerance of lithium ion batteries. It's very interesting. If you operate them in safe limits, nothing will happen. Huh? But the moment you give any kind of abuse that the battery cannot take, it will have this vicious cycle of heat increasing and ultimately leading to thermal runaway. Right? So,
Ma'am,
if yes.
I'm sorry for the interruption. Just before you stated that there is some safe limit to be tackled. Can I know what is the safe limit? What is the abused limit in
Yes, we will
EV
come to
sector?
that. Yes, we will come to that. Don't worry. Okay.
And also whether the limit which it was related to BMS or ECU.
Yes, we will talk all about that. Okay. We are
Okay,
going to
ma'am.
come to that. Okay. Yeah. All right. So we are just understanding the fundamentals and we'll go to those limits, etc. and what can be done about it. Okay. So be with me. Yeah. So even if there is a hotspot on one cell, let's say this particular fellow had a internal or external abuse for whatever reason, started becoming hot, right? Now, because this is a vicious cycle, I told you the temperature would keep on increasing and it spreads to its neighbors. So, what happens first is that there would be smoke coming out of the system, and ultimately it will lead to catching of fire. Okay, so slowly and gradually, we will see that the entire system starts catching fire just when there was a hotspot on one cell in the pack. So it is extremely what conducive, so to say. Hmm? All right. So another interesting thing is that, see, there have been fires with the normal automotives, etc. But what is such a big deal with lithium-ion battery, vehicles? The problem is that these are not a given type of fires, for example. So if you have a fire on this table where I'm sitting at, this is a wooden fire. So I know for wooden material, what is the kind of extinguishing agents I require. For example, for paper, trash, wood, textiles, it is class A fire for which water is a good agent to extinguish it. If it is flammable liquids, then maybe not water directly, but water mist has been found to be successful. If it is electrical equipment, some dry chemical you use. If it is a combustible metal, then you would use some foam. If it is combustible cooking material like cooking gas, etc., or oil, you would use aerosol or some kind of an agent, right? But the problem is that a lithium ion battery fire is not any one of this. Okay, it has a metal casing. It has a flammable metal inside the lithium itself. It has electrolyte, which has several toxic gases coming out. So it is not one class of fire on which you can use one agent. It is a mixed class of fire, right? So this is the big problem. So if lithium ion batteries catch fire, it will be very difficult to extinguish them. Some people say it takes humongous amount of water to extinguish them. So if a car catches fire, the best thing to extinguish it, if it's an electric vehicle, it's to put it on a in a pond of water. So submerge it fully. That is not practical. You won't do that to your car, right? So the best thing is that, because it is a big point of contention, that if a fire happens, because these systems, if you remember, are extremely energy dense system. So compared to many other battery chemistries like lead acid, etc., lithium ion batteries are famous because they have very high energy density, right? Now this merit of lithium ion batteries becomes a demerit for a fire safety angle, because in a small space you have more energy and it keeps coming out. So extinguishing it becomes more challenging because we don't know how to extinguish it. Okay, there have been some research where people say that it is a completely unpredictable fire. For example, flames come out. Fire can be large, medium, or small kind of flames. It has flares of burning gases, so it's like projectile flowing out of the system. Okay, sudden explosions happen. The smoke is very prominent, as you can see in this picture. At the same time, the gases which come out from the electrolyte burning, etc., these are fluoride kind of gases. And now these gases are extremely poisonous and hazardous. So even for the firefighting crew, it becomes a very challenging situation to extinguish that fire, because if they go near it and inhale it, it is a big problem. So this is an example of electric vehicle getting charged in Denmark. So this was a Nissan vehicle. It was being charged from a DC fast charger, and everything was fine. Suddenly they noticed some dark cloud of heavy metal particles started coming out with whistling noise of vented gases. So if we have time at the end, maybe I'll show some videos also. I have all of this recorded in the form of videos. And then what started happening was lighter vapor cloud started coming, and then explosion happened and jet-like flames started coming. When the flames start coming, what happened was all the nearby vehicles also caught fire. So this is the challenge. Even if you have parked an electric vehicle and you're charging it, if it catches fire, because it is so intense, the fire, it will make even nearby cars, etc., catch fire. So it's a challenging problem to solve, right? So what are the strategies that people take to prevent this from happening, right? Because once it happens, the vehicle is gone. That is for sure. So what can we do to prevent this? So one is a passive kind of strategy where you look at safety in terms of fire suppression. So if something is happening, you try to cool it down, you isolate it, you do some chemical suppression, or there is inherent safety, which is in the research stage. So before making the battery, you do some material modification. So this does not happen, right? But we are more interested in this project in the active safety approach. Active safety means operational safety. Can I do something to make sure that this system is not catching fire? Huh? So what can I do? I can estimate the state of health of the battery. I can estimate when is the end of life of the battery and not operate it at that time. I can know what is the state of charge so I don't overcharge it, right? And I can do fault detection and early warning. So detect it, isolate it, and remove it from the system. Thermal management also very important. We have cooling, we have phase change material. So other than the battery pack, there is a phase change material coating, which takes that excess energy from the system, right? And then cell equalization is again a very important part, right? So our focus in this project is on the active strategy of safety for the EV batteries. Okay, so there were some real tests that were conducted in in IIT Gandhinagar, where we actually put battery packs on fire. We measured their temperatures, the rate of change of temperature, and used different kind of agents to extinguish it. So we have noticed there was a company who came here and did this test. We supported them with all the test setup, and we found that they were successful only for small battery packs, like a bicycle battery, you know, 100 watt-hour kind of battery. But for larger packs, even they were not successful. This was very unfortunate. So that's why we keep saying that once the battery catches fire, it is very difficult to extinguish it. For smaller packs, they were able to extinguish it in a few 100 seconds. But but if it is a bigger pack like a car, even their agent is failing left, right, and center. So the idea is, can we do something before the fire actually starts? Huh? Once we know that something has gone wrong, can we prevent it from going into a critical eventuality, losing lives, etc.? So one thing after tremendous literature review and industrial review we found was before the battery starts fire, some smoke starts coming out of it, right? At least there is a few minutes of gap between the fire and that first vent of gases. So, you know, just like a pressure cooker, when there is your khichdi is about to be ready, it releases some steam, right? Or when you are boiling potatoes, it releases the steam. So you know if there are two whistles, my potatoes are ready to be eaten. So just like that, every lithium ion cell has a vent. So when there is internal heating, this electrolyte evaporates, and the evaporation of electrolyte makes this vent rise up and these gases come out. So looking at the composition of the gases, we can find out if these gases are leading to some kind of a fire incident. Okay, so this gas detection has become the the elixir, I would say, of the industry to find out whether an eventuality is about to happen. So this is for different chemistries and different abuse conditions, you will have different signatures of these gases coming out. And if we can have some kind of gas detection, we can, at the first venting itself, like I told you about the pressure cooker example, you can find out whether there is a few minutes or a few seconds before the incident, some eventuality is about to occur. Okay. All right, so for NMC, which is a very popular, highly energy dense chemistry, we see that it has some volatile organic compounds, some hydrogen, some carbon monoxide, some carbon dioxide. Also, we saw for LFP, these concentrations are different. For LCO, these concentrations are again different. So the idea is for every chemistry type, we have a signature. Before the fire is about to happen, what kind of gases will come out. But we cannot just rely on this. We have to develop a multi-dimensional approach of safeguarding the system, right? So we have to also talk to the BMS. So battery management system, like I said, is taking care of batteries, life, health, safety. All of this is under the domain of BMS. But BMS conventionally only measures current voltage temperature and tells you maybe what is the state of charge, what is the temperature, what is the power optimization by cell balancing, etc. But it has to, you know, do more. Like I said, I will discuss. So 15 to 35 degrees Celsius is the optimum range in which the batteries like to operate. But very typically in India, especially where I am in Ahmedabad, we have easily 50 degrees Celsius ambient temperature, right, in the peak of summer months, and we have high humidity also. So how does that affect the working of the BMS, whether the BMS should take active decisions? This not many people have covered, unfortunately. So this is what we thought. Let us take this up as our first showcase of battery safety, where we said we will do something beyond the BMS, right? So we'll have some machine learning, some intelligence as a part of our system, which can predict well in advance what is going to happen to the battery temperature if you operate it like that. And if it is running into the threshold of safety barrier, then we prevent it from happening. Okay, so we could have used physical methods for temperature estimation, but the problem with physical methods is that they may be more accurate, but as the battery is aging, their parameters change. So the physical models are not good anymore, right? So data-driven models, however, are as good as the data input, right? In machine learning, we say that better the data, better is the output, or if you give garbage input, you get garbage output. So the beauty of data driven method is that as long as we are getting real time data, our predictions can be extremely reliable. Okay, so that's what we did for and again, another advantage is that if we use a data driven method like machine learning, we are not married to a battery chemistry. For example, today, instead of lithium ion batteries, we have sodium ion batteries. Our methods are equally sound, right? So it is because we are not using the physical parameters as such. We are relying on the data input. Our methods are chemistry agnostic. So that's what we did. I will show you some of the problems that we faced. Okay, typically people only share success stories. I would like to also walk you through the challenges that will happen when you approach these things and then go to the success eventually. So the problem with lithium ion batteries is that at the beginning of life, they are very predictable. Okay, so you know exactly how they are going to behave. But at the end of the life, the behavior completely changes. Okay, so the last 20% of the chronological data you are never able to predict because you have trained your systems on the first few cycles of the battery life, right? But if you are able to intersperse the data, then you get very good predictions exactly on top of the ground truth. But is this practical? Right? I don't think this is practical because you never will have the end of life data of the battery. Because when you're sending the EV on the field, you only have the beginning of life data. So you don't have training done on that kind of data before. So this is a problem. So then we came up with an approach which is very popular in the data science community, which is uncertainty aware machine learning. So what is meant by uncertainty aware machine learning is that when you have good data, you have tighter bounds. So instead of doing a point prediction, you are doing a range prediction. You are saying that my temperature would be 30 degree plus minus 1 degree Celsius. You're not saying it is exactly 30 degrees. So you are bringing some range or some uncertainty in your prediction. All right. So, like I said, in uncertainty aware machine learning, there is this uh, um, problem that when the data is rich, we have tighter bounds. But when the data is not there, we have large bounds. So our range becomes very high. So I would may not say 30 plus minus 1, I will say 30 plus minus 5. But at least I would know whether I'm entering my threshold of 50 degrees Celsius, for example. Right? So this will be certainly helpful, and this will give us mathematical guarantees that our model is going to tell us whether the battery is safe or not, and therefore alert the user. Huh? So for this case study, we have used 18650 lithium ion battery cells. Uh, these were measured over 4 or 5 years for temperature, voltage, current, and the type of profile, whether it is charging, discharging, pulsed, or constant, etc. This is also available open source from the NASA website. So the idea here is that when we actually did this kind of predictions and we use different methods, okay, because the students are very excited about machine learning, they want to use every method that exists. But what we found as a result of all that analysis was that if you use point prediction methods, and you may use ensemble methods, right? People from ML community may be able to appreciate this better. So ensemble methods mean that you have a movie which has great actors, right? You have 10 great actors together. So that is like an ensemble cast. Similarly, in machine learning, an ensemble method means that many great methods are working together. So we tried ensemble methods for point prediction. We tried simple linear regression. We tried decision tree. We tried random forest, which is like an ensemble methods. And we saw that when there is more uh, uncertainty in the data, for example, compared to a constant profile, in a pulse profile, we have more uncertainty. So because of that, our method, the range prediction method, was much better compared to point prediction methods. But yes, when there is no uncertainty, for example, when you are resting the battery or when you are doing reference charge, then there is no point of killing a bee with a big hammer. You don't need Thor's hammer to kill a small fly, right? So you need a heavier method only when there is need, right? Machine learning should also be used with wisdom, right? You need not use it everywhere. So we say simple methods like linear regression, etc., will work. But if you need more accuracy, maybe you can use an ensemble machine learning method. But when you have more uncertainty like pulse loading, resting, charging, discharging, then the best performance is achieved by uncertainty aware ML methods, which is conformal prediction for us, which can give mathematical guarantees. Fortunately for us, the bands that we got were extremely tight. So within 1 degree Celsius, we were able to say this is the accuracy of our method, right? So also, I would like to say that most of the points were within the band. Only a few which were away, they were just 0.3% away. So the results are extremely accurate. And this is again quite light machine learning. This is not heavy ML. So, some of the students in our group are also very, fun. So they made a app out of it. So you could try it. The idea of this app is given a use case for a battery, it could be an electric vehicle or it could be in a house, home storage, or renewable energy battery backup like that. Depending on the condition that the people have, the ambient condition and the loading profile, we will tell you what would be the ideal battery to use. Okay, so this is an app, Tempest, that they have developed. They are also publishing it now. Here, for example, they're showing the small visual that at 20 degrees Celsius, tell me what is the best battery that I should use for the given C rate. C rate is the charge rate, discharge rate, etc. For the given loading profile. This is a Streamlit app. This is a small screenshot which says, okay, out of LFP, NMC, and NCA, tell me which would be the most effective battery for me. And they're saying, okay, 25 degrees Celsius, NMC is best for you for the given load profile. So this is how they are able to, and the approach they have used is LSTM. LSTM is long short-term memory of machine learning method where it is a time series data. So it is the best approach that the girls found. Another very interesting work that the students have done in our group is the initial proof of concept of this multimodal system that I was talking about. So what is happening here is that any kind of abuse, like I said, right, electrical, mechanical, thermal, or chemical. Chemical is when it is exposed to different kind of gases, etc., how the battery behaves. So there is heat generation. If it is more than the dissipation through cooling, etc., there could be rupture, runaway, fire, and explosion. This we don't want, right? So even before this stage occurs, at overheating stage only, like I said, there is venting and smoke comes out. So if we can detect this, or we can measure the pressure across the cell and we can measure that, or we can find the temperature, whether the temperature is high or not, or we measure the voltage. Because of internal short circuit, there would be a change in the voltage. So if we can measure any of these parameters, can we detect that a fire incident is about to happen? That was our motivation. And students actually developed this prototype on very simple DSPs like controller boards. They use STM32 Nucleo boards, and one is for detection, one is for communication with the BMS. So the idea is that it retrofits with an existing BMS. Like I said, we are talking beyond BMS, right? So a solution which can just go and sit with the BMS and tell us that there is a problem. The temperature is gone beyond the safe range. Yeah. So in this example, because they used LTO cells, they are fine till 70 degrees Celsius. So that is the range that they took. Voltage, because LTO have lower voltages, so 3.3 volt. If the smoke is more than 700 ppm or the pressure is more than 380 m, so then they isolate the battery. So they developed a toy prototype on this lithium-ion battery-powered toy truck. They made their entire system, just as a fun project in the lab as an initial proof of concept of our idea, and they were actually able to see that by different sensing of temperature, voltage, pressure, smoke, they are able to save the battery if there is an eventuality. So they actually put this truck batteries on fire and the system was able to save it. Okay. So I took a lot of time, I know. We have last 10 minutes for question and answer, so let me wind up in next 2 minutes. So the idea is, when any kind of abuse happens to the battery, may it be electrical like overcharging, over discharging, or mechanical like a thermal impact, nail penetration, squeezing of the battery, etc., or a thermal abuse, overheating of the battery, too much low temperature. So in very low temperature also battery cannot charge. It has problem of lithium plating. So dendrites, all that get formed and they internally damage the battery, right? So any kind of abuse that can be detected through multiple methods, either just temperature, just gas, just voltage, or all of them combined. So we use this combined approach because it doesn't really take much to put these kind of simple IoT sensors which are talking to each other, right? And based on that detection with a background machine learning model, which we call as our battery digital twin, we estimate the states and we manage the temperature of the system and give a early warning to the user that, see, for safe operation you right now need to disconnect your battery, or if it is beyond that time also, you say just leave the car and save your life. So at least human lives can be saved. That is our motivation. So like I said, these batteries have low tolerance for abuse, which can be solved with real-time health monitoring with some intelligence in the background, which we are calling as battery digital twin. And these battery digital twins correlate the operation to the abuse signature, in a way extending the life of the battery. And therefore, this electrothermal aging diagnosis that we are able to provide in real time prevents the battery fire. Of course, save lives of the users. And another very interesting thing is that, whenever a startup or a bigger company also, they have to put their batteries in an EV on the field, they have to go through some compliance, some standards. Now, the cost of those standards can be extremely high, right? So before they go there and fail there multiple times and extensively spend money, if they have this tool they can in-house test whether their system is safe or not, and only when it is safe they need to take there and certify it. So it can offset a lot of cost of compliance for smaller players. For a bigger company it may not be a big deal, that cost, but for a startup it is a very big deal actually, right? That's what we understood by talking to many EV startups locally. And of course, this would enhance our transition to green mobility. Uh, if you, these are some of the references of the work. I also would like to say that our lab works in multiple dimensions like renewable integration, fast charging of EVs, power electronics for hydrogen, and we make all of this extremely robust by using the power of data, using IoT sensing and AI-based decision making. So that's all. Thank you. If you have any questions, I'll be happy to take them now.
Thank you so much, ma'am. So, any questions, please raise their hand in the meeting and can start with the question answer or drop the questions in the chat box. Yes, please start.
Hello.
Yeah, please go ahead.
Yeah, ma'am, it's Dr. Dheeraj. Actually, I'm asking about the digital pins which are in the in the recommendation nowadays for different smart systems. What is the security concerns and how we can means, tackle them? So, because these are the new thing that is coming in the market for different smart systems, but security is the main concern that has the issue with the any system, because these are digital systems and data is a more secure. Data has to be more secure. So, what's what are the updates on that regarding the aspect of these new policies and security aspect of means cyber security?
Sure, sure. So that was not a part of today's talk, but that's another giant altogether. Our lab also works in cybersecurity area for energy management systems for microgrids and also extended to the energy storage system. So maybe we'll talk about it another time. Today's scope was only safety and reliability. But yeah, it's a 1 hour lecture in itself, you know. So it will not do it justice if I talk about cybersecurity today. But yes, there are ways of like watermarking approaches, etc., that we are looking into to make sure that nobody else catches hold of your data which you don't want to share. You know, there is a very safe communication between the cloud and the BMS. So another discussion topic that is okay, maybe not today.
Okay, madam. Thank you.
Hello.
Yeah,
Can you
please.
Yes. Hi. This is Mohit. So I did see that you have done some ML algorithms on top of that. So just want to understand how much of the cycle data prior that you have to train the ML models to predict something significant that you are predicting right now with certain accuracies.
Sure, sure. So we, like I said, we are very motivated to do sustainable ML. So we used only 150 seconds of data for getting less than 5% MAPE. So MAPE is mean absolute percentage error. So getting 95% accuracy with just 152 seconds of data. So fast estimation, fast capacity estimation, fast temperature estimation. That is what we are up to. Okay, so 152 seconds of data is not much if you see, right? It is a
Right.
couple of minutes.
Right. But you have to train the model before that, right? I mean, that
Not
is what.
really. No, no,
Or is
no,
it?
not really. There
Okay.
are very good
Interesting.
ML models now which can learn the behavior in less time. But of course, it is you have to be mindful that if it is the beginning of life prediction, then the beginning of life data has to be used to train it if you are going for this fast estimation. So you can't say the model was trained on 152 seconds of the beginning of life and you want to predict the end of life. So this 152 seconds should be close to the time. That's why I keep saying real time estimation. So if it needs couple of minutes in real time and it can immediately predict what would be the temperature. But if you're talking about the entire life cycle, so we have
Right.
also trained BDTs with the entire life cycle of the battery. So that is few months of data. So we have both versions. Some people need fast and tiny ML. Some people, which is edge applications essentially. Some people need a full battery digital twin, which can tell anytime, anywhere, how you use it, how it will behave. Then you need entire data set of battery life cycle, maybe 1,000 cycles, depending on the chemistry, right?
Right. Yeah. No, thanks a lot. That's great. By the way, I'm IDGN alumni as well, and
Oh,
happy to catch you. Yeah, catch up to you. So
sure,
thanks a lot.
sure.
Yes, Mr. Mayur Prakash.
Yeah, good morning, Professor Bharadwaj. A very nice and interesting talk. So my question is related to the safety aspect. So if a new cell undergo thermal runaway due to any reason, compared to that, if a degraded cell undergo thermal runaway, which one will be more devastating? So is a
Right.
degraded cell safe? Have you done any study on that aspect?
Very interesting question indeed. So a new cell has less propensity towards thermal runaway compared to an old cell. That I can tell you for sure. But if both of them have already gone to the stage of a fire, so thermal runaway has already occurred, then a new cell will be more devastating because it has more charge inside, because its capacity is more. Because towards the end of life, the capacity shrinks. So the energy density in general is also lesser for an old cell compared to new cell. So a new cell would be more devastating at the stage of thermal runaway. But the propensity to reach the thermal runaway, it is much lower chances for a new cell compared to an old cell.
Okay, thank you.
So, any other questions?
Ma'am, myself, this is Bala. I have a small question on by EV safety. Just now in this session, we completely major focused on heat dissipation and thermal energy of the battery, thermal dissipation of the battery. Is there any other characteristics which has been playing a major role in safety standard? And what are
Can you
the
say,
things have?
yeah, can you say that again? Your voice got clipped for me. Yeah, can you say that again?
Ma'am, we in this session we spoke mainly on heat dissipation and thermal effectiveness of the battery. Can I know what are the other factors to be considered under the EV safety measures?
Yeah, I mentioned in my talk, gas, pressure, voltage, the differential of voltage, differential of temperature, impedance, all that.
Okay.
Mhm. If somebody asked me in the chat, what is AIS 156 standard applicable for BMS or battery? So AIS 156, which came in 2020, it is for battery plus vehicle safety for L category vehicles. L category means light electric vehicles like two-wheelers, three-wheelers. So it came in 2020 for battery and vehicle safety together for L category, okay, light EVs. I think there were two questions about it, so I think I've answered them now.
Hello.
Yeah?
Hello. Am I audible?
Yeah, please.
Thank you for your talk. It's really nice and appreciative. So I have one question, ma'am. Have you done that sensitivity analysis of this lithium-ion battery? I mean,
Sensitivity for what parameter you mean?
in terms of thermal runaway, those things.
No, thermal runaway is the effect. What sensitivity causes are you referring to?
Means because temperature will change, battery temperature will change as we are using battery. So at what temperature it will get fired like that? So can be
Yeah, I showed a slide,
that
no? Yes. So it catches fire. So I had a dedicated slide for this. So it can go up to 900 degrees Celsius also, but the upward trend starts beyond 100 degrees Celsius. Okay. Yeah.
Ma'am, I think it's 2 minutes left for the, and thank you for your talk. It's wonderful talk. It's wonderful to have you here for this platform. And thank you everyone to join this webinar.